Just like the previous lesson, this lesson is going to extend some ideas that you learned early in the course a bit. So it's going to kind of function as half review, half new stuff. And specifically, we're going to talk about categorical variables. And we first talked about categorical variables in chapter 4. So we're going to generalize some of the ideas from chapter 4 to this stuff. So back in chapter 4, we learned techniques for analyzing relationships between two categorical variables. For example, is the likelihood of divorce higher for smokers versus non-smokers? Or is the likelihood of getting cancer higher for bacon eaters versus non-bacon eaters? So things where you have categories. Either you eat bacon or you don't. Either you smoke or you don't. I know that there's some gray area versus how much someone smokes or how much bacon one eats, but if you fall into one of these two categories, is your risk for some other thing higher? So the raw data from categorical variables consist of group or category names that don't necessarily have a logical ordering. So do not. There's no reason bacon eaters should come before non-bacon eaters or vice versa. A two-way table displays the counts of how many individuals fall into each possible combination of categories. This type of table may also be called a contingency table. The row percentages are the percentages within a row of a contingency table. They're based on the total number of observations in that row. And the column percentages are the percentages within a column of a contingency table. And they're based on the total number of observations in that column. And when looking at two categorical variables, we're interested in whether a relationship that is observed in the sample can be used to infer that there is a relationship in the populations from which the samples were drawn. And this question can be answered using a chi-square test. And the symbol for that is sort of like a curly X with a squared on it. Note, this is not a variable. I've seen people try to take square roots of it, and it's not like X squared. It's just the name is called a chi-square. And here are the 5 steps in a chi-square test. So the first step is to find the null and alternative hypotheses. The null hypothesis will be that the variables are not related, and alternatively, it will be that the variables are related. By default, this is always two-sided. Okay, then summarize the data into an appropriate test statistic after first verifying the necessary conditions are met. If at least 80% of the expected counts are greater than 5 and none are less than 1, then compute chi-squared by doing observed minus expected squared over expected, where you compute the expected values using the row total times the column total divided by what I called the total or total n in the entire table. And remember, do not round off these things to whole numbers. Our general practice was to keep 2 decimal places. Step 3, find the p-value by comparing the test statistic to the possibilities expected if the null hypothesis were true, using the chi-square distribution with degrees of freedom, and in this case it's r minus 1 times c minus 1. Back in chapter 4, we always had 2 by 2 tables, and I just said, oh, well, the degrees of freedom is this magical thing that's called 1, and plugging 2 rows, 2 columns into the formula gives you degrees of freedom equals 1. What we're going to do here that's different than chapter 4 is we're going to have tables that aren't just 2 by 2. Decide whether the result is statistically significant based on the p-value. Choose a significance level alpha. The standard level is alpha equals 0.05. and then report your conclusion in context. So the table we're going to use here is something table A.5 in your text, which I'll also attach to this lesson. And we're going to provide a range for the p-value from the table, and then we'll also use software, which for me is going to be Excel. And just for those of you that have Macs and don't have Excel, numbers, it works pretty much the exact same way. And if you need help figuring out, just get in touch with me. Okay, so chi-squared 3.84 degrees of freedom equals 1. We'll look in table A.5, and you find that the p-value is equal to 0.05 in this case. And since that one exists in the table exactly, we're not going to worry about how you use Excel to do it. All right, chi-squared equals 2.28, degrees of freedom equals 9. Well, looking at the degrees of freedom equals 9 row, you see that the smallest chi-square is 8.34. And if you're looking at that row and you go to the other side of, and as you go this direction in the table, the p goes down. So if you were to go backwards more, the p would be bigger than whatever the p-value is for that number. So your p-value is bigger than 0.5. And that certainly is enough to reject your null hypothesis. So that would be what I would be calling the p-value range. Now to find it exactly, in Excel, you'd type in equals chi.chi_dist. And then you put in your chi-squared value, comma degrees of freedom, and this gives you 0.986. So you go to a cell in Excel, type in this thing, push equals or push enter, and it should give you this. Make sure you can make that happen. I'm pretty sure the command is like the exact same thing if you're using numbers. Here we have a really big chi-squared, and I didn't tell you the degrees of freedom, so you've got to figure that out. R minus 1, C minus 1, so 2 minus 1 times 3 minus 1 is 1 times 2, or 2. And in the df equals 2 row, the biggest chi-square is 13.82. And the p-value for that is 0.001. And so if your point is going to fall on the other side of that, your p is going to get even smaller, so your p is less than that 0.01. And that 0.01 once again came from this guy. Now using Excel, p is equal to chi_dist, put in your chi-squared value, put in your degrees of freedom, and you get 0.0000019. So that's the exact, and this is your range. And you can check, does the exact match with what you found in the range? Is this exact value smaller than that 0.001? And the answer is, of course, yes it is. All right, let's do a review. So this is going to be a problem you could have done back in Chapter 4. So in the 2008 General Social Survey conducted by the National Opinion Research Center at the University of Chicago, participants were asked whether or not they favored the death penalty for a person convicted of murder, and whether or not the use of marijuana should be made legal or not. Here is a two-way table of counts for the responses to these two questions. Okay. So first, let's calculate row and column percentages. So with these row percentages, make sure you kind of keep things in the same order. Favor, oppose, legal, not legal. So here we take our total out of our row. So of the people who favor the death penalty, 313 out of those 774 think marijuana should be legal. That's about 40.4%. And of those who favor the death penalty, 461 out of 774, or 59.6%, think that marijuana should be not legal. And notice that with a row percentage, the total across the row is 100%. Of those who oppose the death penalty, 165 out of 412, which is 40%, think that marijuana should be legal, and the remaining 247 out of 412, which is 60% approximately, think that marijuana should be not legal. So those don't look so different. Let's do the column percentages next. So legal, not legal, favor, oppose the death penalty. So now our total is the column. Okay, so of those who think marijuana should be legal, 313 out of 478, which is about 65.5%, think that marijuana should be legal, and 165 out of that 478, which is 34.5%, oppose the death penalty. So that's how those people who think marijuana should be legal feel about the death penalty. And what the not legal people? Well, 461 out of 708 of them, which is about 65.1%, think that favor the death penalty. And 247 out of 708, which is about 34.9%, think oppose the death penalty. So state null and alternative hypotheses about the two variables that have been used to create the contingency table. So the null hypothesis is that these two variables are not related. So the two variables are opinion on death penalty and opinion on marijuana legalization are not related. And HA says that they are. So opinion on death penalty and opinion on marijuana legalization are related. Next comes a step that takes a while. So find the chi-squared statistic. This will involve a couple steps. The first step is to find the expected values. Remember, this is row total times column total divided by total. And you should verify that you get the same things as me. I am just going to tell you what I got. So we have the favor, we have the oppose, we have the legal, and the not legal. And actually it won't be very hard to show you these. So row total, 774, 478 over 1186. That came out to be 311.95. Notice that's awfully close to what you actually saw of 313. Next one, 774 times 708 out of 1186. That comes out to be 462.05. And remember, one way to check is to check and see if these two numbers add to 774. And they do, but you could check that on a test. Next one, 412 times 478 out of 1186 comes out to be 166.05. And then the last one, 412 times 708 out of 1186 comes out to be 245.95. Okay, then the chi-squared statistic, remember that's the sum of the observed minus expected squared divided by the expected. So in this case, we have 313 minus 311.95 squared over 311.95 plus 461 minus 462.05 squared over 462.05 plus 165 minus 166.05 squared out of 166.05, and then plus 247 minus 245.95 squared over 245.95. Now, sometimes on your tests, I see you guys and you like compute this thing, write down the answer, compute this thing, write down the answer, compute that thing, write down the answer, compute that thing, write down the answer. That is a really inefficient way to do your work. You should try to type this in one go. So put in this thing plus, put in this thing plus. Some calculators don't have enough space for that, but you could say put in the first two things, and that's going to be your answer, and then to that, add the next two things. But look at ways to improve your efficiency with your calculator use. This is one thing that's kind of crappy about calculators on phones is they tend to be not very good at letting you put stuff in all at once. So get a TI-80 something, and that will probably be a lot better. Casios also are kind of funky. So in the future, I'm going to have to require a specific calculator for this class. So chi-squared should come out to be 0.017. Now that you know that's true, take this your calculator and try to prove it to yourself. Don't just accept it. Like, punch that in a calculator and try to do it the most efficient way possible. As in, without writing anything else down except for this expression, because then I can see that you have the right idea. Okay, use that chi-square statistic computed in part C to find a p-value or p-value range. First of all, our degrees of freedom is 2 minus 1 times 2 minus 1, which is 1. And this chi-squared isn't in the table. I mean, there's nothing that small there. So our p is going to be bigger than 0.5 based on the table. Using Excel, p is equal to chi-dist, put in your chi-square statistic, 0.017 degrees of freedom, and you get 0.896, which is a very unimpressive p-value. Form a conclusion and write it in context. Well, we're going to fail to reject H0 at alpha equals 0.05 level, because the p-value is too big. There is insufficient evidence to conclude that there is a relationship between the variables, which are a relationship between opinion on death penalty and marijuana legalization. So we just can't conclude anything's going on. Back to the drawing board. Okay, next we have a table that's a little bit bigger than what we usually use. So let's see how this is different. And in principle, it's not, it's just more tedious. So first, we have the 2001 Youth Risk Behavior Surveillance System. Students were asked how often they wear a seatbelt while driving. Possible choices were never, rarely, sometimes, most times, and always. For this exercise, we combine the responses for never and rarely, and for most times and always, and ignore the sometimes responses. They were also asked about typical grades. So here's a table that summarizes the results. So we want to figure out our grades related to seatbelt use. So the null hypothesis is no relationship. So grades and seatbelt use are not related. And HA is that grades and seatbelt use are related. Okay, now the big work. Find the chi-squared statistic. So instead of 4 things, this time we're going to have 6 things. So same idea, first thing you have to do is find the expected values. Let's just move that up so we have some more space. Okay, so we have the A/B students, the C students, the D/F students. And I'm going to call this most always and call that rarely never. Okay, for those in the most always, well, the row total there is 1534 times the column total, which is 1847 over 2192. That comes out to be 1292.56. In the rarely never, row total 1534, column total 345 out of 2192 comes out to be 241.44. And you can check and see, do those add up to 1534? And they should. Next one, row total 553, column total 1847 out of 2192. That comes out to be 465.96. And this one, 553, 345, 2192, comes out to be 87.04. So the idea is the same as our 2x2 tables, there's just more stuff to work with. 105, 1847 out of 2192, that comes out to be 88.47. And lastly, 105 times 345 out of 2192 comes out to be 16.53. And these are what you'd expect to see if there really was no relationship between these variables. So you can see that they're a little bit different than what you actually observed. And the chi-squared statistic is the thing that quantifies how different that is. Okay, so chi-squared. Observed minus expected squared over expected. So 1354 minus 1292.56 squared over 1292.56 plus. Next we have, let's go across the column. So 180 minus 241.44 squared over 241.44 plus 428 minus 465.96 squared over 465.96 plus 125 minus 87.04 squared over 87.04 plus 65 minus 88.47 squared over 88.47, and then plus 40 minus 16.53 squared over 16.53. Now, you should make sure that you get the same thing when you punch this in a calculator. I get chi-squared is 77.776. So practice punching that in efficiently so when you do your test, you can actually do so. Use the chi-square statistic computed in Part C to find a p-value or p-value range. So first of all, the degrees of freedom, rows minus 1, columns minus 1. Well, there are how many rows? 3 rows, so 3 minus 1 times 2 minus 1 is 2. And there's nothing as big as the chi-squared equals 77.776. So our p is smaller than 0.001. And using Excel, if you type this in, chi-dist 77.776 and 2, it actually straight up at least gave me 0. So basically the number is so small that this effectively just says the p-value is 0. So decide whether the result is statistically significant. Well, since p is less than 0.05, we can reject h0 in favor of HA. And what HA said is that typical grades and seatbelt use are related. So there's a relationship between statistical significance and sample size. And here it is, a larger sample size makes it easier to establish significance. And you will see this in a homework problem. You're basically going to take a set of data that has the exact same row and column percentages, just the numbers are scaled up, and you're going to see that with the larger sample size, proportions that were not significant all of a sudden are when you have a larger sample. So the results of the specific nature of a relationship from a chi-square test should be accompanied by some other descriptive and inferential statistics. So some examples might be descriptions of row or column percentages. That's going to give the reader an idea of how different this actually is. So is the difference large or small will be displayed in the row and column percentages. You could also make bar graphs, and you could also examine these observed minus expected squared over expected, and you can see which ones are sort of the biggest ones, and they're the ones that are the most different from what you expect. And we could also find confidence intervals for the proportions or for differences between proportions. But all of these things take some time, and the most common thing I'd ask of you probably is that one. And one last thing I'm going to teach you that you can totally use from now on and forever. If you have a 2x2 table, there is a shortcut for getting chi-squared. And this shortcut, you will not have to find expected values. So no need to find table of expected values. And the shortcut only works in this little 2x2 case, but so you can use it in those cases. And so here's the shortcut. So the chi-squared statistic is given by n, which is your total, times AD minus BC squared over a product of C1, C2, R1, R2. And I wrote parentheses where I did on purpose. You really do need to have parentheses here and here. And it shouldn't matter in the numerator, but just be extra careful when you put them there and there. And the degrees of freedom here is 1 because we're working with a 2x2 table. So, and then A, B, C, D are the entries in your table. N is the total, which makes sense. C1, C2, column 1 total, column 2 total, R1, R2, row 1 total, row 2 total. So let's refer to the example about the death penalty and marijuana where we found that chi-squared was 0.017, and let's do it using the shortcut. So chi-squared is, well, the first number in the formula was n, which is 1186. And then we have AD, which are these two, 313 times 247 minus 461 times 165, that thing's squared. All that divided by, parenthesis, 478 times 708 times 774 times 412. And put this in a calculator, and you should find that this is also 0.017. And once again, I recommend trying to do this in one go. Don't do intermediary steps. Punch it in one go. And also brackets, same thing as parentheses, so they mean nothing different. So my advice is to use this if you have a 2x2 table to save time. Otherwise, you have to find expected values. But it's a great little shortcut if you can use it.